Hi everyone, so this is a video doing the examples for chapter 11.4 of the year 1 statistics and mechanics book, and this is on using integration. So far in chapter 11.2 we were using differentiation, and we learnt that we can find velocity functions by differentiating displacement functions, or we can find acceleration functions by differentiating velocity functions. The way I like to remember these two facts is that velocity I learn from science when I'm in secondary school, that velocity is the gradient of distance time graphs or displacement time graphs, or speed is the gradient of a distance time graph. And we also learn that acceleration is the gradient of a velocity time graph. So I just remember those facts in my head. We're going to use these two facts to derive two more facts. So, and these are going to involve using integration. So I'm going to multiply by dt on both sides. So I'm going to get v dt equals ds. Now if I integrate both sides, I'm going to get s, because if I integrate ds I get s, and then I get the integral of v dt. And this is a fact that we're going to use in this subchapter, that if I integrate a velocity function, I can get displacement functions. I'm going to do the same thing over here. I'm going to multiply by dt on both sides and get a dt equals dv, and then I'll integrate both sides, and if I integrate dv I get v. And this is our second fact, that if we integrate an acceleration function, we can get the velocity function. So what I tend to do is I just memorize these first two. I memorize that velocity is the gradient of a distance time graph or displacement time graph, and acceleration is the gradient of a velocity time graph, and then I just derive these two from that. Or you can just remember all four. So there are two examples in this subchapter, so we'll do the first one now, which is example 6. And this is on page 188. So example 6, it says that we have a particle moving on the x-axis at time t equals 0. The particle is at a point where x equals 5. So our initial displacement is 5 meters. So at time t equals 0, it's at the position x equals 5. So our initial displacement, and I show that by s with a subscript of 0, and that's 5 meters. The velocity of the particle at time t seconds, where t is greater than 0, is 6t subtract t squared. So they've given us a velocity function. Notice that's a quadratic. And they've given us a restriction on t of t is greater than or equal to 0. So personally, when I solve these problems, I like to draw a plot of what this function would look like. So I can see that this is a quadratic. I'm just going to find the roots of the function so that I can plot it fairly accurately. So if I factor out a t here, and then I get my two solutions, t equals 0 seconds and t equals 6 seconds. So that means that this plot is going to be crossing the axis at 0 seconds and 6 seconds. Another thing to note is that this is a quadratic, but it's not going to be following like the U shape. It'll be an N shape because it's a negative t squared. So 0 and 6 seconds, and then here is our function, so an upside down parabola. I haven't drawn this bit here because t must be greater than or equal to 0, but I mean, if you draw that, it's not the end of the world. So this is what the function looks like when plotted. So part A wants an expression for the displacement of the particle from O at t seconds. So part A, we want the displacement. And we know to find the displacement, we have to integrate the velocity. I'm going to integrate the velocity function. Now, if I integrate the velocity function, then I'm going to have t squared, and then when I divide by the 6 by 2, I get 3. And then I'm going to have t cubed, and when I divide 1 by 3, I get a third, plus c. To find my constant of integration, I use my starting condition that at t equals 0, so at my initial displacement is 5. So all of this is equal to 5 when t is 0. So this term will be 0, this term will be 0, and we'll only be left with c. So the function for the displacement is 3t squared, subtract a third t cubed, plus 5. My plot hasn't helped me yet. For part B, it wants the total distance of the particle from its starting point when t is 6. So, firstly, it asks for the distance, which is a positive, it's a scalar quantity, so it must be positive. It also wants the distance of the particle from its starting point, so that's when t equals 0, to the point when t equals 6, which is over here. Now, another fact that we learn earlier on in our mathematical lives is that displacement or distance is the area beneath a velocity time curve. So we want the area of this part of our graph, only up to the condition of t equals 6. And we also learn in pure maths that to find the area under a curve between two limits, you integrate between those limits. So to get this distance, we are going to integrate the velocity time curve between the limits of 0 and 6. We've already done the integration, but we can just literally write that down. So we've already integrated the function, and now I just need to evaluate the function when t equals 6, evaluate the function when t equals 0, and subtract. Now when t equals 0, we're going to have 0, 0, and 5. So I can put that in pretty quickly. To evaluate it when t equals 6, I will use my calculator to do that. And I get 41. And then 41 subtract 5 gives us 36 metres. So the distance travelled between 0 and 6 seconds is 36 metres. So that's example 6. Example 7. We have a particle travelling in a straight line. After t seconds, its velocity is given by 5 subtract 3t squared with the limit t is greater than or equal to 0. Find the distance travelled by the particle in the third second of motion. So again, I'm going to make a plot of this to just see what I'm working with. And again, they've asked me for the distance, so I have to make sure that my answer is positive. Now, in the previous example, I got a positive answer, and you can see that the area above the curve, well, the area is above the curve, it's a positive area, I guess you could say. So I didn't need to adjust this answer, I didn't need to make it positive, it already was. You'll see in this example we have to do some adjusting at the end. So I'm going to make a plot, and that means I need to find the roots. So to get the roots of this curve, I'm going to make it equal to 0 and solve. So I have I'll have 3t squared equals 5, so t becomes the square root of 5/3, or plus or minus, and that is 1.29 seconds. So I'm going to draw a plot of this, and again, like, this is a quadratic, and the quadratic will be an upside down parabola because we've got negative t squared, and it will also have a y-intercept of 5. So I just need to make sure I draw this as accurately as I can. And t is greater than or equal to 0, so I'm not really too concerned with what's going on in my negative t area of my curve. So I have a y-intercept of 5, and this is going to be an upside down parabola, so it's going to be doing something like this. That's not very neat, but that's what it's going to do. And it crosses the axis here at the positive root 5/3, or 1.29, blah, blah, blah. So that's the plot. Now, we want to work out the distance travelled by the particle in the 3rd second of motion. So the 3rd second of motion, because I want to work out the distance travelled, I'm going to integrate my velocity. And the 3rd second of motion, I just need to make sure I get these limits correct. So I usually just make a little note somewhere, maybe I'll do it in the margin, that from 0 to 1 seconds, that's the 1st second of motion. From 1 to 2 seconds, that's the second second of motion. And from 2 to 3 seconds, that's the 3rd second of motion. So the 3rd second of motion is between the limits 2 and 3 seconds. A common mistake is to put between 3 and 4 seconds as your 3rd second of motion. So we're going to integrate the velocity between 2 and 3. Now, if I show what that looks like on my plot over here, remember root 5/3 is about 1.29. So 2 is going to be after that. So let's say 2 is here and 3 is going to be over here. So when we integrate between these limits, we are going to get this area here. And you'll notice that this is below the x-axis, so we're going to get a negative. And that's because velocity is a scalar quantity, and therefore displacement is a scalar quantity. So displacement's allowed to be negative, but we will have to adjust that and make it positive. But this is essentially what we're looking for, this area here, the distance between 2 and 3 seconds. So I'm going to integrate the function, so I'll have 5t, subtract, and then my t squared will become t cubed, and dividing by 3 means I have no coefficient, and then we don't need to worry about the constant of integration when we're integrating between limits. So this is what we have here. And then I'm going to evaluate this function at 3. I might do it below. So evaluating this function at 3 gives me negative 12. And evaluating this function at 2 gives me 2. So I end up with negative 14. And that's because when you integrate velocity, you get displacement. So the displacement of the particle between 2 and 3 seconds is negative 14 meters, but the distance travelled will be a scalar quantity, will be positive. So the distance travelled in the 3rd second equals 14 meters. So that's how you answer this question. Now, exam questions are usually trickier than this. Exam questions might say, work out the total distance travelled in 3 seconds. Okay, so this isn't in the textbook, but I'm going to do a kind of extra part of this question because exam questions usually are much more complicated. So if I want to work out the distance travelled in 3 seconds, so literally from 0 to 3 seconds, okay, So I want the area from here all the way up to here. Okay, I want all of this area. But remember, distance is a scalar quantity. So this area between 0 and root 5 over 3, that's going to be a positive area. Great, because distance is positive, that's going to be positive, so it's fine. Now, the area between root 5 over 3 and 3 is going to be negative. So actually, I will end up with this, subtract this area. And that would be my displacement, but I want the distance. So in these questions, when you need to work out the distance travelled, and part of your function is above the x-axis, and part of your function is below the x-axis, you have to do them completely separately. So I'll show you how to do that. So we're not just going to integrate between the limits 0 to 3, okay? We're not going to integrate in between the limits 0 to 3. Because I'll have a positive area and negative area and they will cancel each other out. What I need to do to work out the distance travelled is I'm going to integrate between 0 and root 5 over 3. Okay? And that's going to give me this area. And then I'm going to add that to the integral between root 5 over 3 and 3. But remember, this is going to turn out to be negative. This is going to be a negative area, so I need to make it positive. So I'm going to find the magnitude of that. Okay? So, I think the easiest way to do this is to evaluate your integral at these different limits. Okay, so 5t subtract t cubed at the limit 5 over 3, root 5 over 3. I'll calculate that now. So 5 multiplied by root 5 over 3, take away root 5 over 3 cubed. Okay, and I get, I'm just going to keep all of this in exact form, 10 root 15 over 9. If I evaluate this integral, if I evaluate it at 0, it's 0, so I'm not going to bother writing that down. So evaluating it at 0 is 0. Evaluating it at root 5 over 3 is root 5 is this. Then looking at my next integral, I've got root 5 over 3, and now I'm going to evaluate it at 3, which I have already done actually. So evaluating it at 3 gives me negative 12. Okay, so I'm going to use some, I won't use colours, but I've got these two integrals here. Now this one is going to be 10 root 15 over 9. Take away 0, which is fine, it's just 0. Now this is one that I need to be careful with because I want the magnitude of it. So it's going to be negative 12, subtract 10 root 15 over 9, and whatever that turns out to be needs to be positive. So I get 10 root 15 over 9 here, and I'm adding that to, now I'm just going to type this in the calculator and show you, negative 12, take away 10 root 15 over 9, gives me negative this, but that has to be made positive because we are dealing with distance. This area, we said at the beginning, this is going to be negative, and look, it is. It's like negative 16 something. it travels negative 16 metres between this second and between root 5 of 3 seconds and 3 seconds. But because we want distance travelled, we make that positive. So we're going to add this to, I'll keep it in exact form even though it doesn't look very nice, 108 plus 10 root 15 over 9. And then adding those together, so plus, oh actually no, I'll just do it separately. So 10 root 15 over 9 plus 108 plus 10 root 15 over 9 gives us 20.6 metres to 3 significant figures. So, like I said, this isn't in the textbook, but exam questions will often get you to do this. They will get you to integrate over, find the distance travelled, where part of that distance will be down in the negative area, and you need to find the magnitude and add it on. So just be aware of those questions when you do exam problems.